Blood count. This is counting the various blood elements, RBCs, leukocytes, and blood platelets. The conventional method is done by the haemocytometer, which is formed of diluting pipette and counting slide. The volume of the diluting pipette differs in the different blood elements, but the counting slide is the same. The diluting pipette is formed of a bulb and a narrow tube, graduated according to the blood element which is counted by it. Its upper end is connected to a rubber tube to help sucking the blood. The diluting pipette for RBCs has a large bulb provided with a red bead to mix the blood with the diluting fluid, which is saline. The pipette is graduated with mark half at the middle of the tube, 1 below the bulb, and 101 above the bulb. The diluting pipette for leukocytes, on the other hand, has a small bulb containing white bead to mix the blood with the diluting fluid, which contains equal volumes of 2% acetic acid to destroy RBCs and 0.5% gentian violet to stain the nuclei of leukocytes. The pipette is graduated with mark half at the middle of the tube, 1 below the bulb, and 11 above the bulb. The counting slide is provided with a central depression with a depth equals 1/10 millimeter, which represents the height of the counting chamber, or the distance between the cover and the slide. The surface area of the base of this depression equals 1 square millimeters and is divided by 20 lines vertically and another 20 lines horizontally into 400 small squares. The surface area of each small square equals the length multiplied with the width, that equals 1/20 multiplied with 1/20 equals 1/400 of square millimeter. The volume of each small square equals the length multiplied with the width multiplied with the depth, that is 1/20 multiplied with 1/20 multiplied with 1/10 equals 1/4000 of cubic millimeter. This is the volume of each small square. Each 16 small squares are grouped into one large square to facilitate counting. The number present in a single cubic millimeter equals the number present in one small square multiplied with 4,000. Red blood count, or RBCs count. This is counting the number of RBCs in 1 cubic millimeter. This could be done by electronic method, where recent electronic counting devices are now used in hematology labs to automatically count the red cells in blood samples. Conventional method is another method for counting RBCs using the haemocytometer to count the number of RBCs in a single cubic millimeter. Steps: prick the cleaned thumb with a sterilized needle to bring a drop of blood. Suck the blood drop with a diluting pipette till the mark half if we are going to have 200 times dilution, or to the mark 1 if we are going to have 100 times dilution. Then suck saline till the mark 101 and shake well to mix the blood with saline. The blood is then diluted either 200 times if we are going to suck blood up to the mark half, or 100 times if we are going to suck blood till the mark 1. The diluted blood is powered on counting slide and covered by a cover slip. We have to count the number of RBCs present in a single small square. Then by multiplying this number with 4,000, then with the dilution, we get the number of RBCs present in 1 cubic millimeter. But this is quite difficult, as small squares are too small to count RBCs in them. Therefore, we have to count the number of RBCs present in at least 5 big squares. Each big square contains 16 small squares. Then, using the following equation, we get the number of RBCs present in 1 cubic millimeter. The number of RBCs present in 1 cubic millimeter is counted from the following equation. If the number of RBCs present in 5 big squares counted equals n, then by dividing this number over 5 multiplied with 16, which is the number of small squares present in a single big square, then we get the number of RBCs present in a single small square. Then by multiplying this number present in a single small square with 4,000, then with the dilution, we get the number of RBCs present in 1 cubic millimeter. Finally, the end result of the equation is that the number of RBCs present in 1 cubic millimeter equals the number of RBCs counted in 5 big squares multiplied with 10,000 if we are going to use 200 times dilution, or the number counted in 5 big squares multiplied with 5,000 if we are going to use only 100 times dilution. Leukocytes count or white blood cells count. There are two methods of counting leukocytes: the total leukocytic count and the differential leukocytic count. The total leukocytic count is the total number of leukocytes present in a single cubic millimeter. This count is done by the Haemocytometer, which is formed of diluting pipette and counting slide. In total leukocytic count, a special diluting fluid is used, which is formed of equal volumes of 2% acetic acid to destroy RBCs and 0.5% gentian violet to stain the nuclei of leukocytes. Steps: prick the cleaned lump with a sterilized needle to bring a drop of blood. Suck the blood drop with the diluting pipette till the mark half if we are going to have 20 times dilution, or to the mark 1 if we are going to have 10 times dilution. Then suck a special diluting fluid till the mark 11. Shake well to mix the blood with the diluting fluid. Blood is then diluted either 20 times if we are going to suck blood up to the mark half, or 10 times if we are going to suck blood up to the mark 1. The diluted blood is powered on counting slide and covered by a cover slip. The leukocytes present over all big squares are counted, that is, over 1 square millimeter. If the number present in all big squares equals n, then the number of leukocytes present in a single cubic millimeter is counted from the following equation. The number of leukocytes present in a single cubic millimeter equals the number counted in all big squares, that is, the number present over 1 square millimeter multiplied with 10, then multiplied with the dilution. Finally, the end result of the equation is that the number of leukocytes present in a single cubic millimeter equals the number counted in all big squares, or over 1 square millimeter multiplied with 200. If we are going to use 20 times dilution, or the number counted in all big squares multiplied with 100 if we are going to use 10 times dilution. Differential leukocytic count is the percentage of the individual types of leukocytes relative to the total number. Steps: make several blood films and stain them with Leishman. In order to make a good blood film, we have to bring 2 clean slides, then put a drop of blood on one slide and spread with the other by putting it with an angle 45 degrees centigrade over the drop of blood, then spread quickly outwards. A good blood film has to occupy at least 2/3 of the slide. Several films are examined field by field, and the numbers of the individual types of leukocytes are registered in a table form on a sheet of paper. The individual types are identified by their size, nuclear, and cytoplasmic characters. Several fields should be examined until the total number of leukocytes counted reaches at least 200. The percentage of any type of leukocyte is counted from the following equation. The number counted in the column of that type divided by the number of leukocytes in all columns multiplied with 100. Importance of differential leukocytic count. It helps the differential diagnosis of certain infections. For example, neutrophils increase in acute infections. Eosinophils increase in parasitic infections. Lymphocytes increase in chronic infections. Platelets count is the number of platelets present in 1 cubic millimeter. It can be determined by 3 methods. Electronic method is a recent electronic counting devices now available in most of hematology labs in order to easily count platelets in blood samples. Direct method. It is done by the Haemocytometer using the pipette of red blood count. The diluting fluid contains anticoagulant citrates to prevent aggregation and clotting, and brilliant chrysal blue to stain the granulomer or chromomer of the blood platelet. Steps: suck first some of the diluting fluid to prevent adherence of the blood platelets to the wall of the pipette. Then suck blood up to the mark 1. Then suck the diluting fluid till the mark 101. Shake well to mix the blood with the diluting fluid. Pour the diluted blood on the counting slide. and covered by a covered slip. The count is done in the same principles of RBC's count, but the blood is diluted 100 times only. The number of blood platelets in a single cubic millimeter equals the number counted in 5 pig squares multiplied with 5 thousandths, the same principles as in RBC's count. Indirect method. Steps. RBC's count is made first by the haemocytometer. A blood film is done using citrated blood, stained by brilliant chrysal blue to stain the granulomer or chromomer of the blood platelets. Count 1,000 RBCs from the blood film and get the number of platelets present in between, in order to know the proportion between platelets and RBCs. The number of platelets present in 1 cubic millimeter equals the number of RBCs counted by the haemocytometer multiplied with the proportion between platelets and RBCs, that is, the number of platelets counted divided on 1,000. Blood the following table summarizes the blood groups A, B, AB, and O. Possible, but also there are many phenotypes which are of clinical and antibodies they possess in their serum. Group O, only one subtype O, genotype OO. There is no antigens on RBCs, but in the sera there is antibodies for both group A and B. Group A has two subtypes, A1 and A2. The genotypes are combination of either A1 or A2, or sometimes A1, A2, or A1 with O or A2 with O. The genotypes are A1, 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 A2, A1O, A2, A2, A2O. The antigens present on RBCs are either A1 or A2, or sometimes combination of both A1 and A2, as O has no antigens on RBCs. The antibodies present in the serum for all the subtypes are antibodies for B group. Group B has only one subtype, B. The genotypes are either combination of B together or B with O. The genotypes are PP or PO. Antigens on RBCs are only for B, as O has no antigen on RBCs. Antibodies in the serum are antibodies for A group. Group AP has two subtypes according to the subtypes of Group A, A1P and A2P. Genotypes are also two, A1P and A2P. Antigens on RBCs are also A1P and A2P. There are no antibodies in the serum. Clinical features of the different blood groups. Group O is a universal donor or a general donor. This is because the serum of the donor is greatly diluted by the serum of the recipient. Therefore, the antibodies in the serum of the donor are of little importance, but the danger is in the liability of RBCs of the donor to be agglutinated by the serum of the recipient. This cannot happen in O group because it has no antigens on its RBCs. The reverse occurs in group AP, which is a universal or a general recipient because it contains no antibodies in its serum, but only antigen A and B on RBCs, so it can give blood to itself only. Gene of group O is recessive to genes of group A or genes of group B. On the other hand, group A or group B are not dominant to each other. If the father is group A and the mother is group B, some of the offsprings are group AP. This is called codominance. Clinical importance for determination of blood groups. Blood transfusion with the blood of the donor should be of suitable group and must be free from diseases such as hepatitis, AIDS, and syphilis. Medico-legal importance to identify the blood groups of the parents and the children. RHESUS factor or Rh factor is an antigen which has been discovered in the RBCs of rhesus monkeys. It is also found in the RBCs of human persons in a percentage of 85%. Those persons who possess Rh antigen in their RBCs are called Rh positive individuals. Other persons who possess no such antigens are called Rh negative individuals. When an Rh negative person receives blood from an Rh positive person, he will develop anti-Rh bodies in his plasma. This is quite dangerous for the second transfusion of blood from Rh positive persons. When an Rh positive man marries an Rh negative woman, the fetus will be Rh positive. The first child will come without any complications, but during labor, some of the fetal blood Rh positive will pass to the mother's circulation. The mother's blood will start to form anti-Rh bodies. In the next pregnancy, these antibodies will cross the placenta to be mixed with the fetal blood, causing hemolysis of his RBCs and intrauterine fetal death, a condition which is called erythroplastosis. For treatment of these mothers, they have to be injected after each delivery or each abortion with a preparation of anti-Rh. Bone marrow is a specialized connective tissue of reticular type. General characteristics. Classifications. There are two types of bone marrow, red or active bone marrow and yellow or inactive bone marrow. Red or active bone marrow is found in cavities of bones of embryos and children. In adults, it is found in the epiphyses of long bones, flat and short bones. Yellow or fatty or inactive bone marrow is found in shafts of long bones of adults. It is yellow due to its high content of fat cells. Structure of bone marrow. It consists of stroma of reticular connective tissue, blood sinusoids, and two types of cells, fixed and free cells. Fixed cells have no phagocytic powers and do not give rise to other hematopoietic cells. They contain both reticular cells with large pale nucleus and irregular branched cytoplasm and fibroblasts responsible for reticular fibers formation. Free cells include All cell types normally found in the bloodstream, together with their developmental stages, as erythroblasts, myeloblasts, and myelocytes and mature cells. Also, there is some connective tissue cells, as fat cells, plasma cells, and mast cells. Comparison between osteoclasts and megakaryocytes. Shape. Osteoclasts are large, irregular cells with a striated border facing the bony surfaces. On the other hand, megakaryocytes are also large, irregular cells, but with pseudopodia, not a striated border. Structure. Nucleus. Osteoclast has several nuclei, multinucleated, while megakaryocyte has one large multilobed nucleus. Cytoplasm in osteoclast is acidophilic, while in megakaryocyte is lightly basophilic. Site. Osteoclasts are found on bony surfaces in house-shaped lacunae, while megakaryocytes are found in bone marrow. Formation. Osteoclasts are formed by fusion of several monocytes, while megakaryocytes are formed by division of the nucleus without division of the cytoplasm. Functions. Osteoclasts are concerned with bone resorption, while megakaryocytes are concerned with the formation of blood platelets.